The internet is a filthy, filthy place. Make sure your bits are covered up. In this video, we're going to do IPsec. Get yourself all protected across the internet. Make sure that you've got privacy, security, protection. This is Epic Home Tech. My name is Jeremy, and my co-host, Jared.
Hello?
All right, let's get into it. So we're going to carry on from our last little video, where we had our 4 routers set up, and we're going to set up IPsec between left and right across both of our ISPs, making sure that we've got good failover. So let's go ahead and get that started here. All the routers are already operating. Let's get logged in. What is my password? Why is it showing my password in the clear? That was weird.
That was
All right.
weird.
Yeah, I've never seen that before. Exciting experiences. That's what you get with the live stream. All right, so we've got left up and running. And now let's go ahead and get set up in right. Weird. It's not doing it on this one. All right, IPsec. IPsec is a tunneling protocol with encryption and authentication. So the authentication piece is called Ike, the Internet Key Exchange, and we'll be using Ike v2. For anyone out there setting up a new environment, don't use Ike v1. It's not safe, it's not secure. Build from the beginning with Ike v2. There's a lot of additional extensions and features, capabilities in Ike v2 that aren't available in Ike v1. We won't be going into any of those fun pieces like child essays and all these other bits. We're going to focus on a simple tunnel configuration, and we'll go over some of the special the output information that we can see, the keys, the security associations, that kind of bits. So let's get into that configuration. So we've got PGP and we've got our routing already set up. So we should be able to run show route. See that we've got PGP routes. Everything is good to go. Do we see our 10.4? We see our 10.4 and it's going to 10.221. Alright, so we're just checking to make sure that we have a good clear route here. So when we're looking at building our paths, we're going to have this. We're going to have, that's not what I wanted. Delete that. I want you. That's weird. Alright, so we won't be using our cool little canvas. That's a disappointment. So we're going to be building an IPsec tunnel from left in this 10.1 to right in this 10.3. So what I'm checking to make sure is that we are passing traffic to and from over the same path. So to 10.3 we're going via 10.1. So to 10.3 we're going via 10.1. And if we're going to go to 10.4, we're going to go via 10.2. So here's 10.4 and here's 10.2. So we'll have asynchronous routes going from here to here and back, and here to here and back. And we're just going to double check on write just to make sure that all of our assumptions are accurate. So we're on write, and we're going to be sending traffic to this prefix. So that's 10.1. So here's 10.1. And we're going to go to 10.3 via this interface. So going to this prefix, we're going to use this interface on this segment going to this router. If we're going to go to 10.2, here's 10.2, and we're going to go to 10.441 on this interface. So going to 10.2 via this interface on this segment to this router. All right. So we are going to go into security, and we're going to go into Ike. So we're going to start with our Ike configuration. So we're going to set, and the first thing we need to set is our proposal. So in IPSec, each side makes what they call a proposal, and the proposal is your security configurations, your encryptions, your authentications, and we're going to call this AES 256. All right, so we can see that we've got an encryption algorithm, and we're going to do AES 256. Let's try GCM. So where possible, GCM.
There, Jeremy?
So CBC is an older cryptographic algorithm. GCM is the new encryption algorithm using elliptic curve Diffie-Hellman configurations. I am not a crypto analyst. All I know is that those are the right configurations to use where possible. I definitely need to expand my knowledge of those. GCM is also an encryption algorithm that is significantly optimized for x86 or general purpose CPU architectures. Requires fewer cycles to perform the encryption, so it should be significantly faster at a lower CPU burden.
Okay.
And when using these, you should be using Diffie-Hellman group 21, but it's not available. I did actually come across this recently. So 21 is what you should be using, I believe. It's either 20 or 19. One of them is the more appropriate of the options. 24 is not appropriate. So I'm going to do 20. And if it's wrong, I'll just have to edit this video later. Comment on it. Make a correction. And authentication algorithm. And we're going to do SHA 384. You should do 256 or 384. Do whichever is the higher of the two and supported by all of your devices. So we're going to do SHA 384. And what is authentication method? Oh, yes. So here's where we start getting into specifics. So pre-shared keys are pre-shared text strings. So each side has the same pre-shared key. You can do RSA signatures. So here you would choose, you'd set up your RSA signatures, and I think that's set up somewhere else. And we're going to do lifetime seconds, and we're going to do 3600 seconds. Alright, so when using AES GCM for encryption, the authentication algorithm must be set. So here's authentication algorithm. But I did set the authentication algorithm.
It actually says it must not be set.
Oh, it must not. Oh, yeah, failed to read. Hmm. $256. Those RSA signatures. But where are we getting the signatures, or where are we specifying that? Are they pre-shared?
Good question. I think the only thing I've ever set up is the
pre-shared key, right?
pre-shared key, yeah.
Let's look it up. Juniper RSA signatures for IPSec. Authentication method.
Now I gotta hand it to Juniper. Their site is chock full of really good information.
That is definitely true. Their tech library is amazing. So you should be able to find everything you're looking for. Configuring the local certificate for an Ike policy. When you include the authentication method, RSA signature statement at the edit services and all of that. This is for a different device. You must identify a local certificate that is sent to the peer during the Ike authentication phase to configure Ipsec VPN configuration. What device is this set up for? So when you're going through your Junos, they usually tell you what kind of hardware you're looking at. So this is Junos. This is posted March. So this is relatively new. Adaptive Services Interface. This is a different device. It's probably going to take me to the same area. Nope, this is for vSRX devices. Rsa Signature. This was published in January 18, and they're not calling out Ike v2 either. Alright, so RSA Signature looks like it's going to require certificates. Certificates I do not have. We could probably create some, but that might be something for another video. So we're going to go with the pre-shared keys. Let's go ahead and edit into their AES256. Alright, so now we get to set our authentication method again. And our algorithm. LS won't work.
Well, that should be good.
It's not giving me any warning. On this device, I don't believe there's any significant performance difference between AES 256 GCM and CBC, but I'm not 100% on that. All right, so we created our proposal. Next, we need to create a policy. And we're going to call this standard. In larger environments, you might want to give these kind of a versioning so that you can easily switch between different policies or different configurations as you begin to evolve your environment from its initial state with these algorithms, these configurations, to the next stage, something beyond SHA-384. Maybe it's going to be SHA-512, or maybe instead of AES 256 CBC, you're going to go to GCM, or you're going to go to a certificate-based authentication rather than a pre-shared key. So you'll want to have a way to easily change your configurations. You could always just rewrite them completely and then roll back if necessary, but sometimes you want to be able to switch different peers at different times. Maybe you've got a hybrid cloud architecture and you've got a kind of A and B side setup. You can change all of your configurations on the A side, make sure that it's all stable before you change all of your configurations on the B side. So you would need two separate policies to apply to each of the two different IPsec peers. So policy standard. And here's our pre-shared key configuration and ASCII text. And you'll see that once you enter in your ASCII text, it's hashed. However, this is reversible. So we can take this and we can go run, and I think it's request system decrypt password. And there you go.
Nice.
So that is only available on certain ones. So here is your $9. This can be reversed. What you can't do is something like system, and I should not be able to reverse this. But we're gonna go ahead and we're gonna just make sure, because I don't want to expose any passwords. So we're gonna go set system, and we're going to create a quick little user. So login user, and we're going to call this user test. We'll call it test user in camel case. And we're going to go authentication and plain text password. So when you enter in a plain text password, it will prompt you. Now, show system login. We see that there is a password. And if we run request system decrypt password, exactly. That's what I expected. So a $6 password should not be reversible, and at the very least, Junos does not make that an available option for you. It is copy and pasteable, so I could take this and paste it into another Juniper, and the password will still be accepted. This hash is one way, so as you submit your password after you've typed it in the command line, it will hash it one way and then match the hashes, and it should be fine, and then you'll be logged in. But it cannot be reversed. So if this config were to, be dropped on the internet, or if somebody were to take this device from, one of my installations and they decided to open it up, they would get a config that would at least have a pre-shared IPsec key, but it won't have passwords. Anybody can have this hash, and they can go ahead and willingly and happily put it into their devices if that's what they so choose, all that will mean is that somebody can enter a password that they don't know that will give them access. That's just like giving somebody a public RSA key so that they can add it into their known and authenticated accepted keys into their Linux system. It doesn't mean anything bad for you. It isn't good for them though.
Yeah, that's really interesting. $9. I did not know that. That was cool.
System login. I need to set more. We'll just delete this login. All right. So where were we? IPSec, security Ike, and where are we at? All right. Set policy standard. And here you specify your proposals. So in an Ike session, you can propose multiple proposals. And in the negotiation of the Ike session, the two sides will determine what proposals match, and those matching proposals will be the ones that are viable and selected. I don't know how they choose one or the other, but I believe it is a prioritized list top to bottom. I'm not 100% on that though. So we're going to go with a proposal. We're going to go AES 256. I only typically will propose one proposal simply because I'm running both sides and I know what each side has for security, and I've set a standard minimum. I don't believe that you should be accepting less secure proposals just because you can. So there you go. That's my philosophy. Take it or leave it. And we're going to set policy standard. Now, I think by default, I think it's main. So we're going to leave it main. Ike v2, but that's specified later. What else? Do we need anything else? I don't think so.
Oh, I don't think so either.
All right, so we're going to set gateway. And we're going to give it a gateway name. We're going to call this right. And we're going to call it right 1. Because we're going to have two gateways, one for the 000 interface and one for the 001. All right, here we need to specify our Ike policy, and our Ike policy is going to be standard. We're not going to do local and remote identities because we don't need to. Local and remote identities. Local and remote identities make certain things easier to deal with. One of those would be identifying yourself if you're behind NAT. So if your VPN endpoint is behind a NAT, you can use the local identity for the device that's behind the NAT to identify itself, and use the remote identity for the other side. You can, I believe you can omit that, and it will use the WAN interface as the remote identity for the device that is not behind NAT. But the local identity makes some of those pieces easier, so you're always a known entity, especially if you've got multiple devices behind a NAT. But the local identity will usually pick up from your WAN address or your interface's address. The NAT makes things a little bit more complicated. So we won't be going into that part here. Maybe we'll do that in a future video if anybody is interested in that. And if you are, just go ahead and pop comment in the comments below. Alright, so Ike policy is standard. And we're going to go version, and we're going to go v2 only. I believe v2 only is the default, but I prefer to be explicit where possible and we're going to go ahead and be explicit. The only other thing that you must have when you set up a gateway is your external interface. So this is necessary. So this is what ties your IPsec configuration to the appropriate interface. It also helps identify any other misconfigurations. As you begin to work with Ike, there are a lot of different things that it matches up. So as you begin to propose and make your sessions, the local identity will be exchanged within the Ike session. And if you haven't specifically or explicitly stated your local identity, it will take the address from the external interface that I have just specified here, and it will put that in as the local identity. The remote side will see the local identity within the Ike session, and it will compare that to the source address of the traffic that's coming in for the Ike session. That will help it to identify whether or not this is a device behind a NAT. If my physical interface IP address does not match the source address coming into the destination, then there is a discrepancy there. That discrepancy will indicate NAT, and the remote side, if set for NAT traversal, will enable NAT traversal and renegotiate the session with NAT traversal. And NAT traversal is simply taking the Ike session, and instead of using the ISAKEMP protocol, it will switch it into a UDP protocol, and it helps traverse the NAT and maintain the session. Gateway, write one external interface.
That's actually bitten me a couple times where I didn't set the interface at all, and then sat there wondering why I couldn't get anything set.
Yeah. I think it will let you commit with, but I'm not 100% without the external interface. It may not let you commit. If you set it wrong, it will, but it won't do anything.
Yep.
So you do have to specify your unit. I think if you don't specify the unit, it will accept the configuration, but it will never pop. All right, so we've got our gateway configuration in our Ike. We've got our proposals and our policies created. So we're going to go ahead and just do a commit check. Goodbye, Juniper. Take a nap. All right, so now we've created our Ike configuration. So we're going to go up and we're going to go into our IPsec configuration. So Ike is the part of the process that establishes authentication, and it establishes your first what's called a security association. And a security association is where the two sides have authenticated. They've exchanged their initial key material, so that in our case it would be the pre-shared key. So they exchanged what was necessary to get their conversation up and running. Then they negotiated a synchronous key, so a bulk encryption key. They agreed upon that key, and then they established what's called a security association. And that security association is simply an indexed identifier for this particular session that the two sides have agreed upon for their encryption. Once that Ike SA is created, they can then begin creating the IPsec SAs. And the first IPsec SA is going to be the one that we are specifying now in this IPsec configuration. So this takes the Ike configuration and then begins tying it to a encryption configuration that will actually be carrying your traffic, your intended revenue traffic, the things that matter, the things that you're actually building this IPsec configuration for. So here we're going to create, yet again, a proposal. If you are going to work in a multi-vendor environment, the most difficult part in getting it stood up is getting your very first configuration of this multi-vendor setup, this multi-vendor architecture. And the most difficult part is getting both sides minimum configurations to a point where each side can agree on the proposals, the encryption algorithms, the authentication algorithms, all of your what we're going to talk about in a little bit is called the dead peer detection configurations, making sure that all of that lines up for a good stable connection. There's also another thing in here that you'll want to set up called perfect forward secrecy. All of these things need to line up to successfully establish your sessions. Not all of these variables, all of these configuration elements are negotiated in the sessions, like perfect forward secrecy, PFS. PFS is not a negotiated protocol or configuration. You can configure PFS on one side, and you can fail to configure it on the other side. What you will end up with is a session that bounces every time your SA lifetime expires because it wasn't able to negotiate a new key. So it will run right up to the lifetime expiration, then it will terminate the session, reestablish a session, and it will carry on for another lifetime period. Perfect forward secrecy is all about making sure that your next key during a rekey event is secured. And since PFS is not a negotiated thing, it can be messed up. It's complicated. IPsec is not an easy protocol. It's not the worst. It's not the most difficult, and it is doable, but it is not simple.
So let me ask a question, Jeremy. Is there anything for users that are setting this up that you have your ISP1 and ISP2? Is there anything in those devices that could ever prevent, because you may not have control, right, of the ISP1 or ISP2 potentially. Is there anything that would prevent Ike or IPsec, even if you can connect to the left? If that makes sense. Is there anything that could be enabled or not set in these ISP routers that would break that or never allow the connection?
As a typical rule of thumb for internet traffic in the United States, no, there shouldn't be. That's not to say that there couldn't be a misconfiguration or an issue across the internet that would be preventing it. The possibility exists that there could be firewalls or other things between you and them. Let's say we go back to the hybrid cloud architecture. In AWS, you can set up what are called security groups. If your security group is not allowing the right traffic in and out, then your EC2 instance that's terminating your IPsec service won't be able to negotiate the session. If your IPsec device, in IPsec they have two different roles. They've got an initiator and a responder. The initiator is the side that initiates the IPsec session. The responder is the one that waits for it to come in. Both devices can act as both initiator and responder, but when you start talking about scenarios like a hybrid cloud architecture, you're always going to have your remotes be the initiators and your cloud service will always be your responder, simply because your cloud service should be a very static, well-known address and point on the internet. So let's say your initiator is out at your favorite office, and for whatever reason there's a ISP provided piece of equipment to handle the termination of your ISP services and the handoff to you as the customer. They have a firewall enabled in that device for whatever reason. That could prevent an IPsec session. There are other scenarios that could cause IPsec issues, but those are pretty specific, and you would likely have to deal with those as they are discovered or identified in your own environments. But typically in the United States, with US internet service providers, there won't be anything on that path preventing you from achieving a VPN. Now, in other countries, that story is entirely different, where privacy laws and encryption algorithm use is very different.
Okay. Thank you.
I strongly recommend anybody in any other country research what is appropriate and safe for use in your country. I believe some countries do come with a criminal penalty for using certain encryption algorithms. Alright, AES 256, and our encryption algorithm is going to be AES 256 GCM. And I'm going to guess that we don't need an authentication algorithm. So here's protocol, and we're going to go ESP. There. All right. So we see more lifetime, and this is different lifetime. So these are the lifetime settings for the security association. A security association is going to move data, and it will either have a lifetime of amount of data moved, or it will have a lifetime of seconds established. Why would you choose one over the other? With older encryption algorithms, a person could calculate what the key material is once they've collected enough data. So lifetime kilobytes was necessary for older encryption algorithms. It's not so necessary anymore, but I imagine somebody could probably make an argument for the value of it. The common practice is to use lifetime seconds and to specify something that makes sense. You typically want your IPsec lifetimes to be less than your Ike lifetimes. However, that's not necessary in most cases. With most modern IPsec implementations, they will begin negotiating new SAs at about between 50 and maybe 60% of the lifetime's progress. So let's say we were going to set it to 3600 seconds. I believe Juniper starts at 50%. So at about 1800 seconds, the Juniper device will begin keying up a new security associations for all soon to be expiring IPsec security associations. The new security associations will sit and wait in a negotiated but unused state until they begin approaching the lifetime much closer. Then the two devices, or a side of the sessions, will begin making the transition from the current SAs to the next SAs. It does this through specific signaling that the two sides can initiate. In IPsec, the two sides operate independently and they communicate with each other. There isn't an agreed upon, primary or secondary or master and alternate or any sort of configuration like that. It's a multi-master type of configuration. Whomever proposes something first leads the negotiation. So when the left side says it's time to transition our SAs, the right side says okay. and the transition begins to happen. Once they fail over to the new SAs, then they send a delete the old message and the SAs are cleaned up. You typically want your ESP SAs to be less time than your Ike SAs, so you don't have a scenario where your ESP, your IPsec SAs are trying to negotiate at the same time as your Ike security associations. You want them to be kind of off cycle, so that an ESP and IPsec SA negotiation doesn't fail because an Ike association is attempting to happen. It isn't common, but it isn't uncommon. I don't think there's any hard and fast rule of thumb as to what you should and should not do, but do your own research. I will typically do them at the same time just for simplicity. The two sides it will manage those times relatively well. Ike v2 is much better at it than Ike v1 was, and the reason for that is the fact that you can create these SAs that aren't used yet. They call them child SAs. The child SAs can sit there unused and do nothing for their entire lifetime. Ike v2 allows you to have that configuration. Alright, so set proposal AES 256. Shoot, I forgot where we were. Alright, set proposal AES 256. So we set our protocol, we set our encryption algorithm, and we're going to set our lifetime seconds, and we're going to do, we'll do 2400. Just to change it up. Alright, so we're going to set a policy, and we're going to call this one standard as well. We're going to assign our proposal and AES, set policy standard. Here's perfect forward secrecy, keys, and we're going to do group 20. And do your research on the appropriate Diffie-Hellman groups. Anybody setting up significant security type of configurations like this, you should always do your research. Make sure that you understand why you chose what you did and that you've documented it well, so you understand what your risk may be and what risks you may be adopting or accepting in the act of choosing these configurations. Don't let anybody tell you what the right thing to do is without proof or evidence. And even if you choose something that you know is unsecure, like group 24 is known to be less secure and should be avoided where possible, if you have to accept this, understand why and make sure that it's documented. If you have to go through any sort of security reviews, or you operate in an environment where you have a security risk management framework, that these are documented and understood so that all of your security individuals, your security engineers, know what their risks are and can make sure that those are mitigated, or mitigated when appropriate. If you had to choose 24 because 21 wasn't available, then once 21 is available because you upgraded to said version, then begin changing all of your IPsec configurations and ultimately mitigating the risk that you had previously accepted with group 24. Alright, so we got a policy standard, and we've got our proposal. So what else do we got? We're not going to create a manual security association because we don't need to. So we're going to create our VPN configuration. We've got to give it a name, and we're going to call this write1. And I'm going to have to hurry up here, man. We're running. That's pretty long. Long time here. All right. So one thing we will need to have if we're going to create this VPN is we need to identify what our Ike policy is going to be. Our Ike configurations IPsec policy. We are standard, and we need to specify our gateway. I do. Okay, set VPN right 1. And we've got our Ike and our gateway. And definitely use your tab complete. Don't forget about that. We're not going to use proxy identities. This is another one that you're going to have to deal with if you're going to start building a multi-vendor IPsec architecture. Between local identity and remote identity, as well as proxy identities, these are two different solutions for solving certain problems that are created as you begin building multi-vendor IPsec environments. It's how left and right identify each other. In IPsec, they are called left and right, where left is self when you're working on this particular device. So when I am in left, left is left, and when I am in left, right is right. When I am in right, left is right, and when I am in right, right is left. So there you go. Chew on that one for a little bit. But left will always be self.
Listen to that a few times.
Left is always self. Right is always remote. Wherever you're working, you do need to keep in mind the relation and the position, the relativity of what configuration you're trying to work on. And I'll show you what the left and rights are when we look into the output from the Ike session and the IPsec session establishments. All right, so set VPN right 1, Ike gateway is right 1, and I think we've already got our IPsec policy. We're not going to do anything with idle time, intervals, and anti-replay. So anti-replay is a counter that increments continuously on all of your IPsec traffic. That just prevents replay attacks. It's effective enough, so nobody worries about it too much. All right. Oh yes. Oh yes. Ike v2. Ike v2 establishes in Juniper devices a route-based IPsec configuration. So the IPsec tunnel that's created has to be bound to an interface, and that's where you see bind interface here. So that will be a routable interface that you will be able to use in all of your routing policies, routing configurations, static routes, as well as any dynamic routing protocols. You'll be able to specify the interface or the network segment that's used between. So we need to set VPN right 1, and we do bind interface. And when you do the bind interfaces, I believe it's ton 0, right? Is it ton 0 or is it VTI?
I believe it's ton.
Let's check. So let's go top, edit interfaces. And It's not that. It's VTI. That VTI 0 unit. It's not accepting that. The Google machine. I'm pretty sure it was VTI. Juniper interfaces. IPSec. ST0, that's right. I'm drawing up like different devices, different configurations. So since we're here, so ST0 for secure tunnel 0, and we're going to do unit 0, and we're going to give this a description, and we're going to go right 1. And we're going to set ST0 unit 0 family INET, and we're going to give this a network address, and we're going to give it the address of, let's be 192.168 1.0/31. Let's go 0.0 0.0/31. And since we're here, we're going to go units 1 family INET address 192.168.0.2/31. Set ST0 unit 1 description. We'll go right. O.1. We'll set ST0 unit 0 description. Right. There we go. All right, so we've got our ST0 interfaces, our secure tunnel interfaces. Top, edit security, spelled properly, IPSec. All right, so set VPN, right 1. Find interface ST00. All right, and we need to set an IP address. Nope, that was in the gateway. It's supposed to be in the gateway. It's not set. Address, and our address is 10.3.3.2. There is something that we are missing. Set VPN 1, but it's not here. All right, so what other things would we want to set in here? Establish tunnels. That's right, we want to set that. Set VPN right 1 and establish tunnels. So in establish tunnels, you have two different options. You have immediately, which means that as soon as the Ike session is established, this IPsec session will be established as well, and it will remain operational for its lifetime, at which time it will negotiate new keys and it will remain operational. With on traffic, it will key up the tunnel only as long as there is traffic. So on first packet, it will key up the tunnel and then pass traffic. What it typically means is that you end up dropping some of your first traffic each and every time you try to establish the tunnel. However, it does keep the number of maintained security associations down. When you get into IPsec devices enterprise, small devices, across the board, they can only maintain so many security associations before they fail to establish more, either because of memory or they just can't handle things like the constant rekeying. And you can begin crippling your devices if you adjust your lifetimes poorly. So make sure you choose good lifetimes. If you set it to a lifetime of, let's say, 30 seconds, you establish 1,000 security associations. That means that you will be establishing 1,000 security associations every 15 seconds and up to a maximum of 30 seconds. And just the rekeying effort can begin bogging down the CPU to a point where you will start seeing performance degradation. So on-demand is an available option, the on-traffic here. I will typically choose the immediately option, and that gets into more of the other things about how do you monitor all of your devices, how do you monitor your tunnels, especially in an architecture like this where we have a dual MAN architecture. If I have an on-traffic configuration and I don't use all of these tunnels, one of these paths may fail, and it may fail silently, and I won't know until I try to key up this tunnel and it fails. So by being able to have both tunnels up and running all the time, I know that those tunnels are operating and capable of operating when I need them, when I need to fail over to them, or when I need to use them to pass traffic. There's no questions, there's no guessing, there's no concern. They're always available, they're always tested, they're always known. But it does come with the expense of consuming all of those essays, consuming additional cycles and rekeying, and putting yourself in a situation where you've realized what your finite capacity is and there is no flexibility. You do have a known state, but it's inflexible. So there you go. You do have other options. ADVPN is a Juniper, I don't want to say proprietary, but it's also not implemented elsewhere. A dynamic tunneling configuration. Cisco has a similar thing called DMVPN. Both of them are, neither of them are compatible with the other, and they're not compatible with other vendors very well, if at all. So you end up with a vendor lock-in scenario in a non-standard protocol configuration that may or may not have value to you and your project or your architecture, but it's definitely something to consider. It's something to know and understand what it means to your architecture and what it means to your long-term operational supportability. So vendor lock-in is always a thing to consider, and just make sure that it's been considered. You don't want to be surprised, 5 years from now when you're like, I want to switch from Cisco to Juniper, and now I'm stuck with, well, how do I transition all of my IPSec from DMVPN to something else? It's just not the surprise you want. All right, establish tunnels. So we're going to establish tunnels immediately because we don't want to sit around and wait for it to happen. All right, so we're going to go up and we're going to go here. All right, so we see that our Ike configuration has been created. We've got a proposal, we've got our policy, we've got our gateway. Our gateway has an address, we've got an external interface, we've specified our version, we've got our IPsec configuration. Here's our proposal, our protocol encryption algorithm, our lifetime perfect forward secrecy, our key, and our binding of our proposal to our policy, and our policy to our VPN configuration. So here's IPsec policy standard. Here's our gateway that we specified previously, the bind interface for the tunnel that's created, and when do we create it. The one thing that we are missing is an Ike configuration, and we're going to set gateway write 1, and it is called dead peer detection. So our interval is going to be, we're going to leave it at 10. So this is the time between a DPD probe message, and a DPD probe message is like a hello packet. These probes are going to be sent every 10 seconds, and then you can specify what's referred to as the threshold. And the threshold is how many consecutive probes can be missed before it considers the peer dead. So IPsec, Ike are stateless. They don't maintain a hard state with each other with any sort of other additional hellos or like socket binds that would be maintaining a keep alive or a hellos. So DPD helps the two sides identify whether or not the session is still acceptable and valid. This DPD detection is how you configure that. So we're going to be beaconing out at an interval of 10 seconds and a threshold of 3 missed before it considers it dead. This configuration also has an option for optimized. So the optimized option will send probes only when there is no outgoing or incoming traffic, when there's no incoming data traffic. If there's incoming data traffic, it assumes that the peer is still active. This configuration is not uniformly implemented. This is not something specifically defined within IPsec as far as I know. So using an optimized configuration doesn't always translate to a multi-vendor environment well. So it is my practice to skip the optimized and just focus on the interval. It is universally accepted. So stick to that. Stick to the interval.
So effectively, after 30 seconds, it'll just go from established and it'll just change the state. Is that all it's going to do? If
For
I understand
DPD?
it correctly? Yes.
When DPD determines that the threshold has been hit for the number lost, its next action is to reset the tunnel. So it will tear down the entire IPsec session and reestablish it.
Okay. Perfect.
Yep. So it's an aggressive approach and different. So this is another one of those where different vendors handle it differently. Some will choose not to reset all of them. Some will reset for sure. It's all up to the implementation, how it handles DPD. I believe like Strong Swan, you have a choice of what you want to do and in a DPD failure event. Juniper doesn't give you that option, I don't believe, at least not one that I've ever seen. However, I can't think of any scenarios where you would want to keep a dead security association. So, why? Alright, so we configured DPD. DPD is always something good to configure. It is strongly recommended. Any multitude of things can happen on an IPsec session that would prevent it from operating properly. So DPD is a good, solid way to achieve fault detection. There are other mechanisms that you can use that are faster, like BFD, bidirectional forwarding detection. However, BFD is significantly more expensive where it comes to the CPU burden. You can get sub-second fault detection, but that sub-second fault detection means you've got a lot more processing that has to happen. BFD is more or less universally compatible with all major vendors. Juniper, Cisco both support BFD. I expect that many of the other platforms do as well. I do know that both AWS and Azure support BFD, so you can configure it. However, once you configure BFD and you send your first BFD packet, BFD is now fully implemented, at least with AWS. If you choose not to do BFD, I believe you will have to tear down your VPN configuration if configured through AWS directly rather than through an EC2 instance. So keep that in mind as you move forward. BFD, if not configured properly, will default to tearing everything down if it does not succeed. So make sure that if you are going to use BFD, that you have implemented it properly, that you have properly reviewed all of your configurations, and if possible, phone a friend and have them double check it for you. You don't want to take down your most critical network elements, the pieces that you thought were so important that you needed sub-second fault detection, have them torn down because you fat-fingered one number or failed to enable a configuration properly or didn't do things in the right order. Alright, so our Ike looks good. And our IPSec looks good. We're going to go ahead and do a commit check. Alright, so all of that was your IPSec configuration. Once you get your first configuration set up, it's minor tweaks to change and implement on other devices, but your first configuration is going to take you the most time. Recognize that, accept it, and move on. All right. So one thing that you will have to do if you're going to be running this is in your security zones. In your security zones, you will have to set up a new host inbound traffic. So zone, security zone, ISP1, and under protocols, host inbound protocols. No, system services. You'll have to set up Ike. So Ike bundles in all of your IPsec and ESP sessions as well as your NAT-T sessions. So that will permit your Ike session to be established as well as your VPN tunneling. Set zone, security zone, and we're going to set that for ISP2 as well. All right. Let's go ahead and do a commit. And then we're going to take, and we're going to go edit. Slowly chugging away. So we're going to go show Ike. And what we're going to do is we're going to take all of this. And we're going to go. Right, and we're going to go show IPsec. All right, so in this configuration, what we're looking at is pieces that we will need to paste into our other device. So in our other device, we've got a proposal. All of this is correct. Our pre-shared key is $9 and it is copy and pasteable. We have this address, which we'll need to change. Our physical interface will remain the same. Oh, we need to change this. Give everything meaningful names. let's go over here. Edit security Ike. And we're going to do a load merge, and we're going to go put it in from the terminal. So we're going to be loading configuration, merging it into the existing, and our input is going to be through terminal. So there is our configuration. We hit that and watch all of our errors spit out. Why? Oh. Control D. Because we needed to go relative. So since I said edit security and we're positioned within the tree, we need to do relative because we are going to be merging this according to our relative position within the configuration. So now we see that we have loaded all of this in. And we're going to go up, and we're going to go edit IPsec, and we're going to do the same over here. We're going to leave bind interface ST0, and all we're going to do is change this, and we're going to change this. So we changed our VPN name, and we changed our gateway to reflect. So this gateway value needs to match this gateway value. And this is just for our own sanity. So we're going to go load merge terminal relative. All right, now it's warning us that we have an interface reference that's not created. So we're going to go top, we're going to go edit interfaces ST0, and we're going to go .0. We're going to set description, and our description is left 000. We're going to set family unit family inet address, and we're going to go 192.168.0.1/31. So this is where you would put information into your diagram, making sure you're not getting all of your interfaces, all of your numbers confused. Set unit 1, family inet address, 168.0.3.31, and set unit 1 description to left 001. So here, making sure that we're on right, we're setting left. Here's our addresses. We're going to go back over to left, and we're going to go top, show interfaces ST0, just to make sure that we matched up our addresses correctly. So here's our 00. This device is set up with 192.168.0.0.31, and we set ours on this side to 0.131, and we set this one to 0.3 and that one to 0.2. So they are all in the same subnets. Everything is looking nice. All right, so let's go top. Let's go edit security, and let's set zone, security zone, ISP1, host inbound system services Ike, and ISP2. So top, show, compare. All right, so we set up our IPsec configurations, we set up our Ike configurations, we set up our security zones, and we created our two interfaces. So let's go ahead and do a commit check. I'm gonna make sure this all checks clear. I'll commit this.
And about now, you can be very happy that copy and paste exists.
Yes. So I don't have to go through that long process all over again. but like I said, your first configuration is always going to take the most time, even aside from IPsec. It will always take you the most amount of time, your first configuration. If you're working in a larger shop, a bigger enterprise, or a larger architecture, you'll typically start templating a lot of these configurations, and we'll get into that in a future video about templating, different ways to template, especially if you're going to start looking at automation or other kind of NetOps types of tooling where you're going to use something called Jinja 2 templating. Let's commit that. All right. Now we will need to set security, Ike, and we're going to do trace options. And we're going to go file, Ike. And we're going to commit that. So trace options are like setting up your debug configurations. So what I'm doing, I forgot to flag. So when you set your trace options and you specify your file, that's where you're going to write to your debugging information. And flagging is how you specify what you're going to debug. So trace options, flag, and all. So we're going to do this again. All right. So we're going to run, and we are going to monitor start, and that file is called Ike. We're going to run clear security Ike security associations. We're going to clear all of our security associations, and we should start seeing a session attempting at some point here soon. Oh man. Show interface is terse. Alright, so here's our ST000 00000. Security Ike, security associations. Don't have security associations. So I have an idea, but I don't know if it's 100%. So we did fail to put our ST0 interfaces into a security zone. So show security zones. And I think we have a trust one. So set security zones. Trust interfaces. ST00 and 1. There it is.
Yep, that came up quick.
All right, did it come up? Looks like it did. Yep, successfully added SA config. Creating this. Retransmit counts. It doesn't look like it's succeeding. So it failed with an internal error of unknown event. So this looks like it's timing out. Run, monitor, stop. Show security. Ike security associations. Ike. Run, show security. Ike security associations. It already deleted. So here's the initiator cookie, and the responder cookie is a blank. And this is showing the same. So this will typically indicate that it's timing out for whatever reason. The two sides are sending messages, but they're not being received. So let's go ahead, and in your typical scenario, you're not going to have a situation like this. Close those for now. So let's go ahead and let's get this started. So what we might have done is we might have created policies that aren't permitting this traffic, although in an ISP situation they should have been permitting all traffic, but we might have restricted them to ping only. If not, I need to go back and check my security zones, but we're going to double check this just to make sure that our little synthetic environment is set up properly. So we're going to show configuration, security zones, just to make sure we identify what the zones are. So we've got a WAN zone, security policies. And sure enough, here's our WAN to WAN. So what we're going to do is we're going to quick change this application from Junos Ping, and we're going to change it to any. So we're going to go edit security policies, and we're going to delete. Actually, we'll go the other way. Set from zone WAN to zone WAN. Policy permits ICMP match application any. And what you'll notice with a lot of the Juniper configuration is setting something is not mutually exclusive. So I can have an any protocol permitting as well as a Junos ping protocol. So they will stack like that, and that usually indicates a list of things. So you have a list of different applications. Oh, except any. Any is apparently mutually exclusive. So delete from zone WAN to zone WAN. On policy, permit ICMP, match application, Junos ping. All right. Edit security policies from zone WAN to zone WAN. And we're going to delete policy permit all, match application, set policy permits. Oh, it was already there. Match application any. If you have uncommitted changes that you haven't committed and you're attempting to exit, you will be presented with this prompt. Do I want to exit with uncommitted changes? And we're going to say yes, because we don't have any changes we need to make here. So we're going to exit out of that. And this one is done. So we're going to exit out of this one. All right, and we're going to, oh, this console is making noise at me, and I can't handle that. All right. Run show security Ike security associations. All right. Why did you show me twice? All right, so now we see that we have an upstate. We have our initiator and our responder cookies. So everything looks like it's good. We can go and do a detail option. So here is our local and remote. These are our left and rights, depending on what vendor you're talking about. If we go run show log Ike, you will see a very specific notation in here. And it's notation similar to this, but this is the one I'm looking for. But these are similar. So here you see the IP addresses. So these are local identities that are announced, and you see it here. This is actually configured. So these are announced IDs, and once you get into sessions that are actually negotiating, oh, let's get to the bottom here. You start seeing notations similar to this, and all of these are identifying your lefts and rights. When you look at the 500, that means that this is a Ike session. So here are the Ike sessions that are being established. The left and rights help identify what key material is to be used. So when you start looking at things like strong swan or open swan, you're going to have to make sure that these left and rights match. Otherwise, it will tell you that it can't find the keys, or it can't find a proper configurations. And this is all related to that. If these were NAT, you would see additional values in here identifying that this was NAT-T, showing that here is the IP address for the source or destinations, and here is the local IDs that are identified inside each packets. But there you go. So that is your IPsec configuration on the left to right across the ISP1. So we'll set up the other configuration across ISP2, and we'll see both of them up and operational. But first, let's go ahead and test our ping here. So we're going to go show. Oh yeah, and you see this is one of our DPD probes. So it says, "Are you there?" And this is an "Are you there?" ACK. And everything looks good. So your DPD traces and everything is operating as it should. So it runs show route. And since this is a routed tunnel, you see we have our tunnel interfaces, and you see our prefixes. So we can go run ping 192.168, and we should be 0.2. And we get a response. So since we took our ST0 interfaces and we put them in the trust zones, which were already permitting ping, we can get ping passing through. So right now this traffic is running across the tunnel, and you can see that because when you look at your route table again, when we are trying to reach a host within this network, you see that we are traveling across the ST0.0 interface. So via that interface, via that encrypted tunnel, we are reaching our destination. So let's go ahead and set up our other tunnel. So we will go edit, security, Ike. Since we already have some of these configurations in here, the only things that we need to do are go copy gateway write 1 to gateway write 2. And we are going to delete gateway write 2 address. We are going to set gateway write 2 address to 10.4.4.2. We are going to set gateway write 2 external interface to GE0010. So when I set that up, you noticed that I deleted address, but I did not delete external interface. The addresses are not mutually exclusive. You can have a list of addresses for write 2, but we didn't want to have 3.2 in here as well. The external interface, however, is mutually exclusive. You can only define a single external interface. That is non-negotiable.
That's actually nice.
Yes. All right, so we're going to copy VPN write 1 to VPN write 2. And the only thing here is we need to set write 2 bind interface to ST0.1. And that is another mutually exclusive configuration. Oh, we need to set our gateway. Write 2 Ike gateway write 2. There we go. So we're going to go top, show security zones. Let's make sure our zone is set up. So ISP1, ISP2 are set up for Ike, and ST01 is in our trust interface. So we're going to go commits. And we're going to do the same over here to write. Security, Ike. And we're going to go copy gateway left 1 to gateway left 2. We're going to delete gateway left 2 address, set gateway left 2 address to 10.2.2.1. No, 10.2.2.2. And now you can see how I screwed that one up. So delete gateway left 2 address 10.2.2.1. And we're going to set gateway left 2 external interface 0010. Alright, so we see 10.1.1.2, 10.2.2.2, and we see our interface went from GE000 to GE001. We're going to go up, and we're going to get it IPSec. Alright, so we've got our IPSec. We're going to copy VPN left 1 to VPN left 2. We're going to set left 2 VPN left 2 bind interface ST0.1. Set VPN left 2 Ike gateway left 2. Top and commits. Security, Ike, security associations, display, not display, refresh. 2. Alright, so we already see that we've got a responder cookie, and we see that our session is up. Alright, what you'll notice, we've got our remote addresses. This helps you identify your Ike sessions. So if you have a session that isn't coming up or isn't showing in the list, then you have some troubleshooting mechanisms that you can follow through. So what we're also going to do is show security, and we're going to show IPsec security associations. So here are our IPsec security associations. So here we see our sessions. These are our sessions operating right now. So 10332 is our gateway for the remote side. Our port is 500. We've got an unlimited amount of traffic, but we do have time. So here's our lifetime of seconds and unlimited traffic. So this is the amount of lifetime we have remaining on this. These are operating AES GCM 256, so we are operating with our better solutions, our better protocol option, our better encryption algorithm options, and everything is operating as it should. So if we go to detail, we will see that we have all of our information. You see some tunnel events. So it completed. Here's some that failed. Here's our lifetime. Here's our life size remaining, and it's unlimited, so that was that size. The amount of traffic transferred. This is our outbound, and this is, we should have an inbound in here. Yep, so here's our inbound. Here's our outbound. Inbound, outbound. Here's our anti-replay information. It is counter-based. And here's our replay window size of 64. So, anti-replay. Anti-replay is important in that it prevents certain types of attacks against IPsec. However, if your traffic is flowing in a path that is variable or changes, or your traffic is flipping between two paths of different latency, you can arrive at a scenario where some packets after a period of time arrive before another time. So the counter on the packets continues to increment. So if you send a packet and its counter is 10 and the next 20 packets get delayed, so from 10 to 30 those packets get delayed, and you begin receiving on the other end more packets that came after 30, and you will end up with a scenario where your counter has exceeded 64 counts between those 20 packets that got delayed and the later packets. And the 20 packets that were delayed will end up getting dropped because they are outside the replay window. This isn't a typical scenario in most cases. However, if you're running this VPN behind a router that's doing some sort of per packet load balancing across two internet connections, that would be, one, ill-advised, but two, it can create a scenario where one of your internet service providers experiences intermittent latency increases. Those can result in some of your packets arriving outside the replay window, getting dropped, and then you'll end up having to retransmit packets. So you'll end up with a lot of wasted traffic being sent all over the place. So where it comes to IPsec services, try to maintain path synchronicity between your incoming and your outgoing traffics, and just maintaining a low jitter, consistent latency where possible, And if you have a dual WAN architecture, try to pin one of your each of your IPsec sessions onto a specific internet connection, or make sure that it's not flipping back and forth. So we have now operating 2 IPsec sessions. They are operating concurrently, as you can see by our IPsec, our Ike security associations. So both of them are operating concurrently. If these routers were servicing subnets behind them, however, you would only be sending traffic over one or the other. And that's just the nature of the beast. Part of the reason that we can have both of these operating is the fact that they have different remote addresses. That helps enable you to use this dual WAN architecture. If the scenario were that there was a switch here and your right only had one interface, you would find yourself in a scenario where things get a little bit more complicated as to routing, and that's what we're going to look at in our next video, is how do you handle a scenario like that. And it's complicated, but it's not the world's most complicated. It can be worked out. This is one of your common errors, by the way. No proposal chosen. Setting up your IPsec, you will run into this most likely. All it means is that the two sides didn't agree on the proposal for whatever reason that may be. For us, this happened because it timed out. For others, it could be because different proposals were selected, or different algorithms were selected, or the configuration doesn't match properly. So not a huge deal. Just chase it down. It's part of the troubleshooting process of getting IPsec up and running. So in our next video, we'll take, and our right side, we'll squash it down to have one internet connection, and we'll handle that scenario so that we can maintain dual synchronous IPsec tunnels. We'll be introducing a little bit more interesting bits related to IPsec, and we're going to be introducing routing instances and how you manage pathing where you would otherwise not be able to have so many active routes to the same destination. And I think that's it for this video. I can't think of any other great wisdom or knowledge to impart upon you at this stage in the game. So thank you very much for watching. If you enjoyed the video, go ahead and like and subscribe. Leave a comment to let us know how we're doing. And good luck to you.
Thanks.